Okay, so we'll finally finish discussing neural networks. And all of this is just discussing how we train multi-layer perceptrons, which consist of dense layers. We haven't thus far talked about things like convolutional layers or recurrent neural nets, and so on. And hopefully we'll get to that in future lectures. But at the moment, let's just talk about how you can very quickly adapt the previous code that we've used for the iris data set to use for the multi-layer perceptron, so adding layers to that example. So in the iris data set, remember, it consisted of 3 categories, and each of those categories were a different species for the iris plant. This is a very small data set. It's only for toy purposes, for illustration purposes. And we did a training test split, and we trained just a linear classifier with the multi-class logistic loss, which is also called the categorical cross-entropy loss. So we had a layer which, when we construct it, is going to have an output which has 3 different values, and these are the logits for our logistic model. Right. Now let's initialize, so this was the model that we used before, and when we created this model, it has one dense layer which has output size 3, so there's 3 dimension, the first dimension has 3, a shape of just 3 in the output. The input hasn't been set yet. You have to call the model first. So once you call it on some input x, it'll see that this is actually 4-dimensional. Each row is 4-dimensional. And of course, the number of rows is the number of elements of the mini batch. And then, so now model will initialize the appropriate number of variables and be able to, for that dense layer. So it'll create, for example, a 4x3 weight matrix in the dense layer, and so on. We can actually look at the summary, a summary of the model by doing model.summary. We see that it has the one dense layer, and it has a number of parameters is 15. And so that should make sense because it's a 4x3 weight matrix, which is 12 parameters. And then there's 3 intercept parameters, which would bring you to 15. They call it bias parameters in deep learning. Anyway, and so what we're going to do is just modify the model, and actually nothing else from our existing code is going to change. And that's sort of the magic of using these frameworks, is that you can modify these this architecture without any trouble. Right? And so our new model, we're going to use Keris's Sequential API, and all this says is we're just going to specify the layers from top to bottom, which just say the output goes into this first dense layer, and then that output of that dense layer goes in the next dense layer, and so on. You also have to specify the activation function. I'm just going to use ReLUs throughout, but I could have just as easily used sigmoids. So you might want to go back through and just convert these to sigmoids and see what happens. And so if we just look at the summary for this model, we have our first dense layer. Number of parameters here is 50. So if we think about this previous one, it has an input size of 4, an input shape of 4, and an output shape of 10. So there's going to be 40 parameters to the weight matrix that's constructed. And then there's 10 different biases or intercepts. And so 40 plus 10 is 50. Does that make sense? And now you're going to have an output shape of 10 that feeds into something that has an output shape of 3. And 10 to 3 will give you 30 weight parameters plus the 3 intercepts, which should give you 33 parameters altogether. Okay, so that's a summary of this model. Now, how does the rest of our optimization change? Well, the loss, nothing changes about the loss code, right? We're still going to define the sparse categorical cross-entropy loss, and it's still going to take those logits output in. The logits have the same shape because they are just three-dimensional by the number of elements of your mini batch. So nothing about the loss changes. This is also the loss. What about gradients? Okay, so I had this grad def that I got from the TensorFlow tutorial, and it takes in the model. Inputs and targets are just the x and the y variables, and then we're going to initialize a gradient tape so that it starts taking gradients in the automatic differentiation. We're going to apply our loss to the model, inputs and targets, and specify that training was true. But nothing here was specific to a modified model. This is just general for any model. And when I do this, I can take the gradients of that loss with respect to all of the trainable variables, which includes the trainable variables in the earlier layers. We're going to initialize an optimizer just like before, so we'll use SGD. And then we'll call this gradient on the models, the x and the y, to give us a loss value in the grads. Okay, so let's look at what happens when we train this. Okay, so nothing about this code changes either, because when we make the updates, we still output the same. We still use this grad model. These grads will now include the gradients of the first layer, that layer with 10 hidden units. But then so do the trainable variables. That also includes the variables and the hidden units. And so these grads and the trainable variables, they still will match up, even though there's an additional set of trainable variables. So nothing changed here, and the rest of this training doesn't change at all. We're still going to apply the gradients. We're still using this SGD optimizer. So nothing changed here. We can look at the accuracies, and we can look at our test error just as before. We have our test set accuracy is 97.5, which is probably the best we're going to do on this data set. But just for kicks, let's just increase the number of layers, right? So we have dense, dense, dense. But now instead of going right into something with 10 dimensional output, we're going to go into something with 6-dimensional output, then another layer which has 6-dimensional output. So let's just count the number of parameters just to see if this makes sense. So we have our first dense layer has 30 parameters. So it was something that was of shape 4 going into something of shape 6. So we have 4 times 6 is 24. And then there are 6 intercepts, so 24 plus 6 is 30. Great, that makes sense. For the next dense layer, we also have something of shape 6 into something of shape 6. That's 36 different weight parameters, and then the 6 intercepts makes 42. So in the final dense layer, you have it outputting to 3. So that'll make 21 parameters. So this really makes sense. And this actually, even though we added depth, we didn't increase the width. So the number of trainable parameters is pretty close to the previous number of trainable parameters. Another change I made is I used the atom optimizer. So like I said before, there's a lot of different choices like Adagrad, Atom, and just vanilla SGD, and all of them are going to have various tuning parameters and arguments. Atom, with its defaults, tends to work pretty well, at least for the multi-layer perceptron. So I'm just going to use the default parameters. I found that with Atom, I don't have to run nearly the same number of epochs. So I'm just going to set the number of epochs to 40. And very quickly, I get convergence to optimal, the same test accuracy. And then after this, if I continue training, I don't see any difference in test accuracy. And so with this optimization, with the choice of Atom and this architecture, I very quickly get convergence. And so that's another interesting artifact of using a different optimizer, is that because you train much more quickly, perhaps you don't need the same number of epochs that you had before. Okay, so that concludes our talk about neural networks and the multi-layer perceptron. We'll return to neural nets when we talk about convolutional neural nets and recurrent neural nets and text processing. But most of those are going to we're just going to be looking at new types of layers, and all of this training procedure is pretty much going to stay the same. We're just going to talk about when you would use some layers versus others. Okay, thank you very much.